Let us consider the following example of a steady-state converging-diverging nozzle in which 2 kilograms per second of steam enters our nozzle at a pressure of 4,000 kPa and a temperature of 400 degrees centigrade with a velocity of 10 meters per second. The nozzle exhausts to a pressure of 1,500 kPa with a velocity of 665 meters per second. We want to determine our exit cross-sectional flow area. Schematically, we have our converging-diverging nozzle drawn below. M.1 is our mass flow rate entering at state 1, and M.2 is our mass flow rate exiting at state 2. We begin our analysis by writing our state variables. At state 1, we have 2 kilograms per second of steam entering at a pressure of 4,000 kPa and a temperature of 400 degrees centigrade with a velocity of 10 meters per second. We are going to convert this kinetic energy into a velocity such that our pressure at state 2 decreases to 1,500 kPa and our velocity at state 2 increases to 665 meters per second. By our continuity equation, our mass flow rate at state 2 has to be equal to that at state 1. We recognize that state 1 is a superheated vapor based upon our temperature and pressure. We are unsure of where state 2 exists. To begin, we will apply our conservation of energy equation for a single stream device, neglecting work and heat transfer. For a nozzle, it's typically assumed to be insulated and its volume should not be changing. Thus, on a per mass basis, we can divide Q dot, W dot, and our M dot terms by M dot. Since there is no heat being supplied, Q dot tends to 0. No work being done, W dot tends to 0. Our mass flow rates are equal, so M dot 1 and M dot 2 are identically equal. If we divide those out, we are left with unity, and we are going to neglect any change of our potential energies. Thus, our conservation of energy equation reduces to the following. 0 is equal to H1 minus H2 plus V1 squared minus V2 squared over 2. If we rearrange this expression to solve for enthalpy at state 2, we have our enthalpy at state 2 is equal to our enthalpy at state 1 plus V1 squared minus V2 squared over 2. That is, our enthalpy at state 2 is going to be that at state 1 plus the change of our kinetic energy contribution. So, we know state 1 exists at a pressure of 4,000 kPa and a temperature of 400 degrees centigrade. Thus, from our superheated steam tables, our enthalpy at state 1 is 3,213.6 kilojoule per kg. Our velocity at state 1 is 10 meters per second, and our velocity at state 2 is 665 meters per second. Inserting those quantities in for V1 squared plus V2 squared over 2, recalling we have to convert our meter squared per second squared to kilojoule per kg. We make the following substitution and we solve for enthalpy at state 2, which is 2,992.5 kilojoule per kg. If we look at our steam tables based upon our pressure of 1,500 kPa and our given enthalpy, we still exist in our superheated vapor region. Thus, we can pull our specific volume from our superheated steam tables as 0.1627 meters cubed per kg. If we go back to our definition of our mass flow rate being our density times cross-sectional flow area times velocity, which is equal to our cross-sectional flow area times velocity per our specific volume, we can solve for our cross-sectional flow area at our exit, A2, in terms of our mass flow rate, M dot, our specific volume at state 2, nu2, and our velocity at state 2, v2. If we substitute in our quantities, our mass flow rate at state 2 is the same as that at state 1, 2 kilograms per second. Our specific volume at state 2 was found to be 0.1627 meters cubed per kg, and our velocity is 665 meters per second. Therefore, our exit cross-sectional flow area has to be 4.89 times 10 to the minus fourth meters squared.